At this point, you should have a pretty good understanding of the basic metapopulation model. That really serves as a foundation for understanding metapopulation dynamics. And certainly there are lots of variations on this basic model. There are lots of permutations. And there are in particular, two models that build off this basic model that are fairly common that I'd like to run through now. Terry will follow up with another spreadsheet exercise that will, again, incorporate those variations. So the first model is called the internal colonization model. The second one is called the rescue effect model. So what are those things? Let's start with the internal colonization model. In this model, we basically assume that the probability of colonization is not constant across sites. In other words, the probability of a subpopulation becoming colonized is a function of how many sites are occupied. It's a function of F. So the more sites that are occupied, the greater the chance that those unoccupied sites become colonized is. Or we might think of it the other way: the fewer the sites there are, the lower the chance of those empty sites, those remaining sites, becoming colonized. So the probability of colonization is a function of F. And that might actually be a more realistic situation for our marmots and probably for a lot of other species. If we return to our marmots and think about our metapopulation in Mongolia, there's probably not some super source, some super mainland source showering in marmots into our population. Instead, we probably have our metapopulation in which colonizations really are a function of the fraction of other sites that are occupied. So this model is probably a little bit more appropriate. An important point here under this model is that when F is 0, so when the fraction of occupied sites is 0, it means that the colonization probability is also 0. So if we compare that to the mainland island model, under the mainland island system, when we have F being 0, our colonization probability is the same as if our F value was 75 or 80%. So how do we model, how do we capture this internal colonization effect? Is there a way that we can do that mathematically? Well, there is, and a common approach is to really focus on this part, the probability of colonization, of our basic metapopulation model. So we're going to take that model and we're going to modify it a little bit to capture this internal colonization effect. And what we'll do is we'll take PI and we'll substitute for PI this thing here, which is I times F. So we know what F is, right? That's the fraction of occupied sites. And the more sites that are occupied, the greater the chance for internal colonization. And this I term here is a little tricky, but the I term really is a measure of the strength of that effect. It's how strong this internal colonization effect might be. So we might say for I that I is really how much the probability of colonization of empty sites out there in our metapopulation, how much that probability of colonization increases with each additional site or patch that becomes occupied. So this is a term that we probably generate through some observations of our species of interest. So for species that aren't really good dispersers, let's say, those that aren't very good at seeding new areas, we might give them a relatively low value. So a species like a marmot, for example. The marmot's, it's a big rodent, but it doesn't really move all that quickly relative to a fox, for example. So they're not that good at dispersing across the landscape. So we probably give it a lower value. It has a low strength measure here when considering internal colonization. But for a species that's very agile, one that can move quickly and disperse well, we would probably give it a higher value. So we're now going to take IF and substitute that in for our probability of colonization in our basic metapopulation model, the mainland island model, which you recall here is the change in F over time in our system is then our rate of immigration minus our rate of extinction. And you'll notice here I've simply modified that equation by taking what used to be the PI term and substituted in for it this IF term. So in this case, with this new equation that captures internal colonization, we can then do as we've done for the mainland island model. We can estimate what we expect the system, the metapopulation, to be like when it's in some form of equilibrium, when it's not changing from time period to time period. And that has some conservation values. So let's say we want to estimate F, the fraction of sites at equilibrium. And we can do that by, again, setting the left side of our equation to 0. So the change in the fraction of sites over time in our system is 0. It's unchanging, it's stable. And that then leaves us with the rest of the equation that I just showed you. So this is I, this part of the equation, and this is E, this is the extinction part of the equation. And all we're going to do, as we've done before, is use a little bit of algebra to solve for this F term. And so the algebra here is pretty straightforward, but it may look a little confusing. So if it is a little confusing, what I'd recommend doing is simply writing this equation out and solving for F. Let's go ahead and do that now. I'm going to take this part of the equation and I'm going to bring it over to the other side here of our equation. That gives us now, on the right side, IF times I minus F. Then what I'll do is I'll divide by the F here in order to continue to refine this equation, and that'll give us this new equation here. That's PE equals I minus IF. Got it? So I've just brought this and divided it onto the other side. Okay, so let's take that a little bit further. Here we are just where we left off. And what I'll do at this point is I'm going to swing the IF over to this side, and I'm going to swing the PE over to this side. Again, this is just basic algebra here. And I'm left now with this equation. And when I've got this value here, I'm just going to solve for F by dividing by I. Whew. Sounds like a lot, but again, this is just basic algebra. When we do that then, we have solved for F, and we've given F this little hat here, so we have F hat, and F hat being the fraction of occupied sites at equilibrium under the internal colonization idea, or the concept here. And that ends up being 1 minus the probability of extinction divided by our measure of strength of internal colonization. So that's our I term. Okay, with me so far? So let's put a couple of numbers to that thing. Let's now jump back to our marmots, and let's put some numbers into that equation and solve for equilibrium. So let's say that our I term now is 0.2, and again, that's probably representative for our big rodent here. It's not terribly vagile, not a great disperser, so we've got a relatively low value for our I term here. And let's say that we have in our system, we know that the probability of extinction for sites is 0.4. So here we've got a 20% value, and here we've got a 40% value. So there's a 40% chance that a site will go extinct. So let's take these numbers now and plug them into equilibrium. So we're now back to our F hat equation, the new equation we just put together. And this is, again, to estimate how many sites we expect to be occupied at equilibrium. So we have 1 minus PE divided by I. And we know what PE is. probability of extinction, and we know what the magnitude of our internal colonization effect is. What is the result? What is 1 minus 0.4 divided by 0.2? Well, we know that 0.4 divided by 0.2 is what? It actually ends up being a value of 2. So we have now 1 minus 2, which gives us now negative 1. So what is that negative 1 telling us? It's less than 0. Equilibrium is less than 0, which indicates that all of the colonies, and indeed the entire metapopulation, will go extinct under this scenario. Next, let's consider the rescue effect model, which again is another variation on our basic mainland island model. But under the rescue effect model, we have a different assumption. We assume under this model that the extinction probability, so the extinction probability of a subpopulation, is now a function of f, which is different than the island system, right? The mainland island model, in which probability of extinction is constant. So in this case, it's not constant, it's a function of f. So the more sites that we have occupied within our metapopulation, then the likelihood of extinction, the probability of extinction, actually decreases. Why might that be? If we had lots of sites that are occupied, we have potentially lots of dispersers, lots of potential colonists that are being sent out by these various subpopulations. And the more colonists that are out there means that if we have one subpopulation that's on the verge of going extinct, it stands a much greater chance at being rescued by one of those colonists. So when we have lots of sites that are occupied, extinction probability is a little bit lower. There's a greater chance of being rescued by some colonist. If we have few sites that are available, let's say there's only a couple that are occupied, then the likelihood of extinction actually goes up quite a bit because there are fewer colonists being sent out into the system. So extinction depends on F. Let's look at this in a little bit more detail. How do we capture the rescue effect, let's say mathematically? Well, to do that, we'll basically take our probability of extinction term and modify it a little bit. We're going to change that term, and we're then going to substitute that change into our basic mainland island model. And that then will allow us to account for this rescue effect. And once we have that new equation, we can estimate, again, at equilibrium, what we expect the system to be like at a stable state over time. So we'll start here with probability of extinction. And we're going to change that term to the following, E times 1 minus F. So we've got this new term here, which is E. And in some ways, it's similar to the internal colonization model that we just covered, in that E is kind of a measure of the strength of that rescue effect. So we might call it how much the probability of extinction of a site decreases with the addition of another occupied site. So as more sites become occupied, how much does the probability of extinction decrease? So it's again a measure that we would use to capture the strength of that rescue effect. So we can take this new value and substitute it in. We can substitute it into our basic metapopulation model. So we go back to that basic model, and we've got again the change in the fraction of sites that are occupied per time in our system is the immigration rate, which is, of course, this term here, minus our extinction term, which used to be probability of extinction times F, and now we've placed E times 1 minus F in that position. To solve for equilibrium, to estimate the fraction of occupied sites at equilibrium, Given this rescue effect, we then set the left side of that equation to 0, just as we've done in the internal colonization and mainland island models previously. And then we have our equation, which we just left. And with that, we will solve then for f. So we'll use a bit of algebra here to rearrange this equation in order to solve for f. Easy enough. If you get tripped up with some of the algebra, write this equation out and solve for f on your own. Pretty easy though. So we'll start by taking this part of the equation and bringing it over to this side. So we'll add it to this side, and that now gives us EF times 1 minus F. And that will then equal the remaining portion of the equation. So I'm going to divide now by 1 minus F, and I will cancel this out, and it will also cancel this out. So we now have EF equaling PI. And if we want then to solve for F, we simply divide now by E, and that gives us the fraction of occupied sites at equilibrium. So remember, we put a little hat on top of F in order to indicate that we're now interested in equilibrium, is the probability of colonization divided by our measure of this rescue effect. Make sense? Is that easy enough? So let me turn you back to Terry, who will show you how to build these two models into your spreadsheet.